Can you draw the resonance structures? There is electron deficiency, as we talked about. If there's electron deficiency, things can move around, right? That's what we discussed. So can you draw the resonance structures? How many people think yes? Even all of you think no? I mean, except you. Actually, resonance structure cannot be drawn. There is a vacancy here, but around it, these are all, there's no lone pair, no multiple bonds. So there's nothing to move. So no resonance structures can be drawn. What that means is this carbon, it has to handle that electron deficiency 100% on their own, on its own. But what about the other one? Now there's electron deficiency right there, but next to it, there's a double bond. Can we draw the resonance structures? You see the differences between these two? It's not just this. You're going to have these two combined to be able to draw the resonance structure. Yes, this is kind of example we already talked about. Double bond next to the positive charged carbon, this position of double bond is not specified. All because these electron pairs making double bonds can move in to the single bond, and then they make a double bonds here. What that makes it, that makes this carbon not having a double bond becomes a positively charged. That's the reason positive charge move. So that's the where resonance structures can be drawn. What about this one? I got electron deficiency there, but I don't see any double bonds. So you cannot draw the resonance structure. So think about what I said. What can move around? Electrons in the multiple bond and lone pairs. There is a no multiple bonds, but we have a nitrogen with a lone pair. That lone pairs of nitrogen, it can come in between two carbon and nitrogens and makes a double bond. That makes a nitrogen positively charged. I mean, that charged state, if you're not be sure which one gets charged, which one's not, then you probably need to use the formal charge formula that we talked about last class to figure it out. But anyway, it can make the resonance structures because the nitrogen is a lone pair. So it's not just double bonds, triple bonds. It's also the more, the other heteroatoms that can never rotate. In this case, that's going to be the major. The reason why this becomes the major contributors is that carbon has just 6 electrons. It doesn't have an octet field. If you look at the nitrogens, how many electrons in nitrogen? So it says a 1, 2, 3, 4 bonding. So each bond is a 2 electrons. So total 8 electrons. So what that means is, even though these are positive charges, nitrogen is an octet field, carbon is octet field. Compared to that one, we have a carbon octet not field. So between these two, what's more stable? This is the way more stable. It's all about octet that we talk about. Because it only has a 1 hydrogen there. If it's a 2 hydrogen, then there will be no positive charge. So anyway, so that's kind of the things that you need to be able to do. It's a good question. Moving on, I got pages of this question to go over. So let's just go a little faster because we have to go to the affinity-based concept. That one, can you draw the resonance structures? We got double bond, right? So electron pairs can move around. But if you're going to move it around, you're going to make this positive charge, that's going to be negative charge, making a charge separation. Yeah, we can potentially draw the resonance structures, but it is not really good one. So that's too bad, actually. So I'm going to ignore that. But anyway, this is not going to move around any direction because you got saturated carbon here, saturated carbon here, saturated carbon here. You just cannot, electron cannot move around without the electrification somewhere. But this one is a different, right? It's the same situation we just talked about. Yes, there's an electron deficiency, it could move in, so you are making a resonance structure. That's the same situation we just talked about. But we only talked about the positively charged carbon. What about it's a negatively charged over there? Then can you still make the resonance structure? If you're thinking about moving electron this direction, then no, clearly no. Because if you make this electron moving into direction, then you are making this carbon having a 10 electron. That's bad. So resonance structures cannot be drawn. Probably conclusion that you're going to get to. But I'm going to say, yes, you still can make a resonance structures. Very valid point in this case. Why? Because this is not the only electron that can move around. There's electrons on that carbon too. Carbon being negatively charged, what that means is this carbon has a lone pair. Don't have a hydrogen attached. It has a lone pair. That lone pairs can move. Not that double bonded carbon moving this direction. These lone pairs actually coming in down here. It's at the other electrons making a resonance structures. 9 electrons are coming in. If you just stay like this, you're going to make this carbon 10 electrons. So that's binding octet rule. So what you do along with that, you're making electron pairs coming out and make this carbon having a negative charge. So resonance structures still can be drawn, but you're drawing it with the different electrons first. Not going this way, it's actually coming the other way. So that's why so many different possibilities. We cannot just make a statements that you should do this, you should do that. There's no flow chart here. You just have to analyze the whole thing together. Right? We talked about not only just the carbons, but sometimes like nitrogen, oxygen, those lone pair can't be used for making resonance structures. Let's just talk about it one more time. Can you draw the resonance structures with this? There's a lone pair, right? That electrons can move around. But there's no electron deficiency on that carbon. There's no electron deficiency anywhere. So what it means is that lone pairs from the stay on nitrogens, you cannot draw the resonance structure. What if you got this? Can you draw the resonance? If the double bonds moving in these directions, if you think about that way, then no, you cannot draw the resonance structures. But we already talked about these nitrogen lone pairs can move in, making a carbon nitrogen double bond. But if that electron pairs go up, then you can draw the resonance structure. That is the form that we should talk. I mean, we just talked about it. And the previous example with the carbon with the negative charges. It's just not negatively charged carbon, it just read the nitrogen with the lone pair. That's only difference. But anyway, so that can form. And then between these two, I would say that's a major form, that's minor form. In the previous example, we talked about the carbon with the nitrogen with the positive charges. I mean, carbon with the positive charges. That has a octet flat field carbon here. But this one and that one, this one doesn't have any charges at all. This is actually all the carbons are octet field, all the nitrogens are octet field. This is the most stable form compared to the other one. Even though this one, if you count the octets for the nitrogens and carbon, all of them actually have an octet. Nitrogen has octet field, carbon has octet field, even though it's negatively charged. But what makes this one minor compared to that? Charge separation. Nature doesn't want to get charge separated. So that's what makes it less stable than this one. All right, that example, what I'm trying to show you, is the same thing. It does not move into that direction. If the pairs of electrons move in that direction, you're going to make the nitrogen carbon double bonded it like this. And then that's going to have a 10 electron nitrogen. That's basically bad. So the second will be, and which is the nitrogen there. What about this one? So, as I said earlier, these positive charges, we are moving positive charges, we are moving electrons. So where the electrons to move is on either double bond or the nitrogens. So if we can do two different ways, but let's say this nitrogen electron moving in, like a nitrogen carbon double bonds here, that makes this carbon 10 electron. So it has to give up if one of the pair of electrons go somewhere else. That can come out like this, but we see the net positive charge right here. So instead of coming out like this, you can simply go make the double bonds over here. So you should be able to combine the movements together. And this is the same question. Between these two, which one should be the major contributor, which one is the minor contributor? You should be able to pick that one as a major contributor, not that one. It's all because, either way, something has to be positively charged, right? We cannot avoid a positive charge going into some places. But what's the difference between these two is carbon has only 6 electrons. This is a not octet field. But if you look at this carbon, the charge is gone, so it's having an octet. But now you may think that the nitrogen is a positive charge. Yeah, sure, nitrogen is a positive charge because it's using its lone pair for making double bonds. But when you count in the electrons in the outer shell, they still have 8 electrons, still have an octet field nitrogen. So that's why octet field carbon, octet field nitrogens. In this case, that's fine. That's octet field nitrogens, but octet not field carbon. So that's the reason why these ones are more stable. That's the major contributors compared to the other one. What about this one? Can you draw the resonance structure? There is a lone pair, there's a double bond, there's a negative charge. There's so many electrons that move around. But it looks like you can draw the resonance structures, right? But this one, I'm saying you cannot draw the resonance structures. Because if you try to do that, going this way, going the other way, it doesn't make any sense. Let's say you make this one electron moving in, make a double bond like this. That electron has to go somewhere. It goes over here, making double bond with nitrogens. Then you're making nitrogen 10 electrons. So that's violating octet. If you go this way, you make the double bond come in, the lone pairs coming in, making a double bond, right? Then this double bond has to go somewhere, it goes between these two, then you make this carbon with a 10 electron. But either way, you cannot draw the resonance structures. So it's not like a similar structure made of resonance structures. So in an exam, I see it somewhere, I'm just going to draw it as I remember it. No, it doesn't work. If you try to memorize how to solve a question in organic chemistry, you mostly going to wrong because we're going to lay traps there. Someone who just memorize things, we always make the question hard enough to you just fall into the trap. You got to solve it out. You got to work it out. You don't just memorize how the math question, unless someone asks you what's the sine values of the 32 degrees, right? That even I don't know. You just have to memorize the number or you have to use calculators. But other than that, you have to drive it. You got to work it out. Move the electrons. Move somewhere. Find out what's the problem. Maybe we can move further. Maybe that can be possible. Maybe go in the other direction. In all those things, you got to work it out. You just cannot memorize it how to solve a question in organic chemistry. That's why I told you organic chemistry is a mathematics for the life sciences. You got to work it out. Right? These two examples, look at that. How similar are those two? That can make a resonance structures. That cannot. I hope that I give you enough example here, but let's just quickly get something done. This one, we got electron deficiency right here, double bonds right here. So these double bond electrons, position can be ambiguous. By having it moving over here, that makes the positive charges go down here. That's a value resonance structures, right? It is almost the same thing as what we talked about. There's a resonance structure can be drawn. So this is what you need to consider. In an exam, if I ask you, draw the resonance structure of this one, and you draw that, because yeah, that's something that I'm pretty sure it makes sense. You need that only. And I'm going to do only 50% right. You're losing 50% of the credit. Why? What did I not do, right? Because I just did what can be done. We already talked about that. Why this is not only thing here, because there's a positive charge next to an oxygen. You can draw another resonance structure. In total, 2 resonance structures possible in this example. It's not always one, right? Electrons can be moved down here, then these electrons of oxygen can move in here, make another resonance structure. The total number of resonance structures in this case, 2. Can it make another one? How many resonance structures do you have to come up with? Do I always tell you how many you draw? And the answer is no. I'm not going to say how many you have to draw. So after, even though you got this, you should question, can you draw more resonance structures after that? All right? Can this positive charge go somewhere other places? This is why we talked about those rules. As long as you don't violate the rule, you can do anything. But this is how far we can go. In order to make this electron move here, I mean, electron can move down here if there's something here, but we see nothing. So there's nothing else can be done. Sometimes you do see something else and it can simply just keep going. But in this case, that's a dead end. So anyway, among these 3, now which one is a major contributor? Which one is a minor contributor? You're going to think about stability. And then the stability of the structures, we talked about 2 things, octets and the charge separations, right? Anyway, all 3 of them having a single charge. It's either carbons are charged or oxygens charged. But we only talked about these things. This carbon has only 6 electrons, octets not filled. That's still the carbon, 6 electrons, octets not filled. If you look at the oxygen positively charged, yeah, oxygen is a positive charge because it's using its lone pair to make a bond. But if you count the electrons in the valence shell, 8 electrons. Oxygen still have an octet field. So that's why these are major contributors, those are minor. All right, next one. The concept of this page is sometimes you can come up with a multiple resonance structure. This one, you got a negative charge down here, that means low pairs on this carbon. That can come in, making double bonds, but that's going to make this carbon 10 electrons. So this carbon has to give up a pair of electrons go somewhere. So that's why it's a 2 electron movement here. One goes down, making a double bond. This pair comes out, making a negative charge right here. So that's the resonance structure 1. If you stop here, you get the half credit again. Because this can go further, because if it comes in between those 2 carbon, if this electron pair is going up, yes, you can draw another resonance structure. And among these 3, which ones are major contributors? Then you're probably going to look for any atom who doesn't have an octet field, right? In this case, these carbons are not octet field because they're positively charged. Positively charged means electrons are not there, right? 6 electrons. This carbon is a lone pair. It has only 1 hydrogen, but it's a lone pair. This carbon has an octet field. Not like the positively charged carbon that has an octet field. This is an octet field. That's an octet field. So all the electrons, there's nothing violating octet rule here. Yet we can still talk about the major or minor, because if you think about it, negative charges staying on carbon, staying on carbon, staying on oxygen. Which elements can handle higher density better? That's a rule of electronegativity. We should punish someone who discovered electronegativity, right? It's been used so many times. Anyway, so that is why this was a major, because oxygen can handle negative charge better than the carbon, a lot better. About 1 trillion times better. So, I mean, on paper, it is like one of the other structures, but in reality, it makes a huge difference which one can be charged. It's almost like you give 100 kilogram baggage, you carry it or your kid carry it. It's different, right? Let's talk about this one. Oxygen is a negatively charged. Can you draw the resonance structure? In order to make a resonance group, this electron pair has to come in here, right? Then this carbon's going to be 10 electrons, so that has to go up. So that makes up this negative charge on the benzene ring. But now the aromaticity is broken. But it's possible. Is that the only resonance group you can draw? No. It can still come in between those two, make the negative charge pop out there. It makes another one. Is this the only one? No, it can come in, make it pop out there. So it can make all in total 4 resonance structures. It's not just 1 or 2. Sometimes it could have 10. Sometimes it could have 20. Sometimes it could have none. So whenever I ask you to draw the resonance structures, if you only draw one, you gotta think more. And you gotta check if you can draw more. If you come up with a 2, you still have to check if there's more possible or not. Right? Because we're not gonna give you how many resonance structures you have to draw. You gotta draw all the valid resonance structures, including the minor. All right, I believe the next one's going to be the last one of the resonance structures. Oh, stability. Stability of among these 4, that's the major contributors, that's the minor contributors for 2 reasons. One, well, we talked about the oxygen being negative charges, a lot of the carbon being a negative charge resonance thing, but there's another big reason behind it. Another big reason behind why these ones are more stable together, that benzene can make a resonance structure on its own, right? This one comes in, that one goes, this one goes there. Very classic benzene resonance structures. What that means is these aromatic structures are not disturbed. But if you look at that one, those aromatic benzenes gone. You're breaking aromaticity, which is a huge penalty to pay. We will discuss the detail a lot later, but that's the 2 reasons why that one is a major contributor. But these resonance structures are possible. So drawing the resonance structures, it sounds simple because we only have 2 rules. Don't violate the octet rule, right? Don't break the single bond. There's only 2 rules that you're going to use to draw them. But it can be used so many different ways. This is not a simple question. And you're going to get this question in the exam. And you should be able to do well until the end of the organic chemistry 2, not just 1. So you should get it right now, or you're going to regret it. I guarantee it. All right, one more thing, and then I guess we're done with the resonance structure. Can you draw the resonance structure with this? And this is something that we already talked about. So this is nothing really means. We know that benzene make a resonance structure. It's a very classic thing you have seen, which can, yeah, these double bonds in the 6-member ring, they're not really specified. That's the reason why the benzene, the bond between the 2 carbons, is not a double bond. It's not a single bond. It's a 1.5 bond. Right? So that's the resonance structures. Is that the only resonance structure you can draw? No, we can draw the resonance structure between these 2. Lower pairs comes in, make these carbons to double bonds. That double bond becomes a single bond with also negative charge. That is basically the resonance structure of the carboxylate. Yeah, that's possible. But sometimes the people draw that and just, yeah, they're going to trap something there. I've got to find more. Just have to find more because that cannot be all. If you just keep going and going, and then you may actually break the rule, you may come up with something that does not make anything. Can you do that? Like this thing comes in, make a carbon to double bonds, but instead of the electron pairs going up, we are breaking this single bond and then make that. Electron movements are right, but as I said, the resonance structures, we're not breaking a single bond. So these electron pair negative charges does not come into the benzene ring at all. This is different from what we talked about here. This negative charge on the oxygen, it can come into the ring and goes around, right? That's what can happen. It looks very similar. Negative charge on that oxygen. Then you may well try to do the same thing with what you see before. It gotta be come into the ring. Because I just seen it somewhere before similar like that. I want to make it get into the ring, and then you're trying to drive it, and then it just comes in and then be there. No, it cannot be possible because you cannot break a single bond. And sometimes you just draw non-structures because you just hopefully find something I don't know, I just draw it without thinking anything. I hope you don't do this at all. No matter how much you wish that negative charge to get into the benzene, in this example, it's isolated between these two, or because you cannot break a single bond. There's no connection. This negative charge on oxygen never get into the ring. There's no way you can draw that resonance structure with that example. It's all case by case. You gotta work out each one separately. That's the message I'm trying to tell you. You cannot memorize that. And if you see something similar before somewhere else, as long as they are an exact same question, you cannot just simply follow the pattern of the solving problems.